Hello, DDD. You're in 3D, you're real. This is amazing. Hello, and welcome to my talk about plain text. Now, the last year or two has been characterized by planning to do things that then didn't happen. And what's happened this weekend is I left the house yesterday planning to do nothing. And then I got a slightly panicked message from Jess going, "Help, can you do a talk?" So I am not Lucy Fletcher, and this is not the talk that is printed in the program. I'm me. This is me, Dylan Beattie. I run ASCII, which is a company I started last year so I could do lots of traveling, and that was a brilliant idea. So I had to do an agile pivot on my business plan, and now I do online training for software developers and technology professionals, and at least some of you have been in some of my workshops, so if you want any more, you know where to find them. I'm a Microsoft MVP with the Developer Technologies program, which is basically Microsoft's, you do cool stuff that doesn't fit in any of our buckets, but we kind of want to keep you anyway. I run a .NET user group in London with a couple of the other London.NET folks who are here today. I also once invented a programming language in a bar as a joke that proved so popular that it is now a joke with a reference implementation and a formal test suite. And if any of you has ever wanted to go on LinkedIn and apply for all those rockstar developer jobs, go to codewithrockstar.com, type in a Rockstar program. The Rockstar programming language lets you write songs that are also, or write programs that are also bad 80s heavy metal songs. That's what's wonderful about it. And you press rock, and if it runs, you are a Rockstar programmer, and you can go out and get all those sweet LinkedIn jobs. And yeah, I'm going to talk to you about plain text. Now, how many of you have opinions about plain text? Because saying, you know, it's like asking fish, what do you think about water? They're like, well, I guess. Like, you know, we don't really stop. We would talk about plain text and plain text files and these kinds of things all the time. But very seldom does anyone actually stop and think, well, hang on, what is this plain text thing that we keep talking about? Now, the fundamental premise of technology and computers that makes them interesting and good and useful is that you can take something that exists in the real world, an idea, a piece of text, some music or video or something, and you can put that idea into the technology, and then the technology can do something with it. It can search it or filter it or send it around the world, and then it comes back out at the other end, and if it worked, the person on the other end of that connection can share your idea, or they can read your text, or they can listen to your song. Now, human beings invented writing about 5,000 years ago, but things didn't get interesting until about 150 years ago. We had the bright idea of what if we could combine writing with this thing we just discovered called electricity. And we invented this, the Cook and Wheatstone telegraph system. Now, this was the first commercial telegraph that was used anywhere in the world. And there's a lot of things about this project. This goes back to about the 1830s. Now, the people behind this project, Cook was a business person and Wheatstone was an engineer. And Cook wanted to sell everything and Wheatstone wanted it to be open source. Does this sound familiar to anyone who's ever done a startup? And the other interesting difference of opinion they had is Cook was adamant that you had to be able to use this machine with no training. Whereas Wheatstone is like, come on, we're sending text over like tens of miles. They can read the manual. Now, the encoding system that they came out with was actually quite ingenious. If you look closely at the sort of dial on the front of this, it looks like this. It had 5 needles, and each of those needles could be connected to an electrical circuit. Now, the Cook and Wheatstone system, they actually ran wire. There was no telegraph network, no phone system, nothing. The first installation of this was between Paddington Station and West Drayton, which is a distance of about 13 miles. So they had 5 cables, 13 miles long each, running between these 2 railway lines. And the way that you sent a letter is you sent a signal down one cable and back along another one, and it would make the needles twitch. And then you looked at where the needles crossed, and that's the letter you were sending. It could only encode 24 characters. It couldn't encode the full alphabet. But this was, you know, we'd never had anything like this before. Up until this point, if you wanted to get a message from West Drayton to Paddington, you had to send it on a horse or on a train. And this was actually, it was used to catch a murderer. About 2 years after it came out, somebody tried to escape from the police by jumping on a train, and they telegraphed ahead, and there were police waiting to arrest this person at Paddington, and that made a lot of headlines. But it's also the first text encoding system that human beings ever came up with. It is a 5-symbol trinary encoding system. We've got 5 symbols, and each one of these can be positive, negative, or neutral. And so to encode a character, you have 0, 0, plus, 0, minus, and that gives you a code. So if you've ever been working with ASCII or Unicode and you're thinking that working with 8 bits is difficult, it could have been a lot worse. We could have ended up with a 5-bit trinary coding system. Now, the problem with Cook and Wheatstone is that it had 5 cables. And eventually one of them stopped working. And they're like, well, shall we run another cable? And let's see if we can come up with an encoding system that only uses 4 cables. And they did. And then one of those stopped working. And they went, 3 cables? And while this is going on, over the other side of the Atlantic, a guy called Samuel Morse is going, 1 cable, 1 single cable, that's all we're going to need. And he invented Morse code, which was a coding system that only needed a single wire. Now, the Morse code that we use today, that was in use for, over 100 years, was not actually the same one invented by Samuel Morse. This international Morse code was invented by a guy called Friedrich Gerke, who was a German telecoms engineer. And they had a conference in 1865 where they ratified Morse code as the standard for international telegraph networks. And then they started building telegraph systems. Now, if you've ever worked in tech, you know that when you have no users, you can change anything you like because nobody cares. But as soon as you started rolling your system or your protocol or something out to production and you have people using it, you can't change it anymore because you're stuck with it. Morse code was so successful that it ran intact for a century. From 1865 until 1965, it was by far the dominant text encoding system that was in use by pretty much every system anywhere in the world that used electricity to do things with text. 1965, things were a little different because we had invented the computer. And the kind of computers that they had around the time, Morse code doesn't work very well for digital information systems because Morse code is a time-based code. You have dots, you have dashes, you also have gaps. And the lengths of the gaps are what gives you the difference between letters and words and paragraphs. And it is very difficult to store lengths of gaps in a binary computer. So we needed a new encoding system, and the American Standards Association, which now is known as ANSI, it was the precursor to ANSI, a bunch of them sat down and went, yeah, we should fix this, we'll design an encoding system, and they did. The American Standard Code for Information Interchange, which all of us are still using in some form today. Now, the thing about ASCII is it was invented to run on these kinds of things. Teleprinters. Most computers didn't have a screen because we'd only just kind of figured out how to invent those. And most computer programs were stored on punched cards. So when you dig into the detail of how ASCII actually works, what you discover is a lot of very, very clever solutions to problems that none of us has had for decades. Let's take a look at it. Now, this is the first block of 31 characters in ASCII. We don't use most of these because these were control codes for mechanical teleprinters, but they do survive in various odd forms. If you wanted to start a heading on your teleprinter, you would send control code 1, which you'd got by pressing Control A. If you wanted to send start of text, you'd press Control B. If you wanted to end the text, you would send Control C. And that survives. And when your program has gone into an infinite loop and you're like, stop running, and you hit Control C, you are sending a signal that was designed to stop a mechanical teleprinter from teleprinting anymore because something had gone horribly wrong. Then there's a whole bunch of inquiry and acknowledgement, and the ASCII control code 7 there, that's the bell, that's Control G. And if you're on a Windows machine and you type echo Control G and you press enter, it will go ping, because that's how we interpret the bell command code now. Then we have interesting things like the backspace. If your backspace key's broken, you can delete things by pressing Control H, which might be of some use to somebody one day. And then we get into line feeds and vertical tabs and form feeds and carriage returns. Now, how many of you end a line with a \r\n when you are writing code? I know I do because I use Microsoft Windows, whereas those of you who use Mac OS will use /n, Linux uses /n, and old Mac OS just uses /r on its own. As I found out last week, Adobe After Effects also still uses /r on its own because I had some JavaScript that just would not work. Now, the reason why these exist is that your mechanical teleprinter has a thing called a carriage. That's this thing here. And to get a new line, you have to return the carriage to the start of the line and then feed the next line through your printer. And you could do clever stuff with this. Like if you print a line and then you do a carriage return and you print the same line again, you get bold because it doesn't line up quite right, and so you get this overprinting effect. And so a carriage return on its own was actually useful on certain devices that existed. Now, as I said, today we have this interesting scenario where some kinds of computers are like /n is fine, and some are like, no, /r/n. And if you're working in .NET, which is where I do a lot of work, we're just like, no, we've just got environment.newline, and that theoretically figures it out. It doesn't always work. The reason why we have this distinction is that Linux and macOS evolved from an old operating system called Unix, which evolved from an even older operating system called Multics. And Multics was the first operating system that had device drivers. It was the first OS in history where the stuff that you were sending from your program could be translated by something, a piece of code that sat between the computer and the device, the teleprinter. And so they had a place where they could go, well, look, when you get a new line, it's obvious you want to go to the start of the next line. So we'll use a /n, and we'll translate that in the device driver into a carriage return and a line feed character. Windows evolved from Windows, which evolved from Windows, which evolved from DOS, which evolved from CP/M, which was designed to run on cheap hardware that didn't have any device drivers. And so that's why, to this day, we have the two dominant operating systems on this planet cannot agree what the end of a line is supposed to look like, is because of backwards compatibility going back to decisions from the 1960s and 70s that we are still supporting today. Now, this next chunk here, this is the punctuation. Now, the creators of ASCII had to make some interesting decisions because they didn't have enough space for all of the characters that were in use in the United States in printed form in 1965. They could get close. Now, this thing here, the hyphen, they kind of went, well, in typesetting we've got hyphens, we've got n dashes, we've got m dashes, we've got minus sign, which is technically not a hyphen, it's a different kind of punctuation mark. But they didn't have enough space for all that, so they just consolidated on a hyphen. And they went, well, open quotes and close quotes, no, we'll just go with straight quotes. So we lost something in the process of standardizing ASCII. Now, the next block here, these are the character codes representing the digits. And one of the things computers got to do a lot is they've got to turn numbers into text and back again. And the way that you do this in ASCII is you just ignore the top half. You look at that, and the bottom half of each of these bytes is the numeric value of that digit, which even on a 4-bit microprocessor, you could do very, very quickly. We get to the alphanumeric block here. One of the nice design features of ASCII, has anyone ever been like, why is capital A 65? But lowercase a 97. Why did they choose those two numbers? The answer is they are different by 1 bit. So if you want to do a case-insensitive comparison in ASCII, you just ignore the 7th bit. And then big A and little a end up the same, and so you don't have to worry about which one is which. And then finally, we have a little bit more, mop up some extra punctuation they needed, and you get ASCII code 127, which is delete. Delete looks like this. The reason delete looks like this is the only way to erase information from a punch card is to punch out all the rest of the holes, so you can't tell which holes were there before. And so the ASCII code delete is the one that punches out every hole on your little 90-column punch card. And if you delete every character on a punch card, the punch card would fall apart and get gummed up in the workings of the mainframe and cause everyone a great deal of mischief. So that's ASCII, 127 characters, 7-bit encoding system. And the Americans turn around and slap themselves on the back and go, good job, everyone. That's enough. That's all they're ever going to need. And the rest of the world goes, what? We can't work with this. Now, my own personal experience of the fact that maybe ASCII wasn't good enough was this thing. Because I grew up in Zimbabwe where they speak English and use dollars and cents, and so ASCII pretty much does the job. And when I moved to the UK when I was 10 years old and I was trying to print my homework from WordPerfect or WordStar or whatever I was using, I could not print a pound sign because the printer and the computer could not agree what a pound sign was. Now, the reason for that, ASCII works great up to a point. We've got 127 characters, but that only uses 7 bits. There's another bit. There's an 8th bit. And so a lot of people around the world simultaneously go, hello? Is anyone using this bit? And of course, no one's got any kind of claim on it. So loads of companies and people and projects independently go, yay, we're going to solve our problems using the top half of ASCII, and all of them are incompatible. All of these different companies and platforms and technology, they're all like, oh no, well, this is what the top half of ASCII is for. And this was the problem with my homework. The computer and the printer had a different idea about what the top half of ASCII was used for. These became known as code pages, an expression that may strike fear into hearts of people who've worked with them. Now, this one is one of the most famous code pages. This is called code page 437. It shipped with the IBM PC. And IBM did some interesting stuff with this. One, they used the top half to support Western European accented characters, to do these kind of box drawing and line drawing characters so you could do ASCII menus. They support half of the Greek alphabet because they didn't care about Greek, but they did care about physics. So the Greek letters which are used in scientific equations made it into code page 437. The rest of the Greek alphabet did not. They did something else interesting. They went, we don't have mechanical teleprinters anymore, so we can use the top block, the first 32 characters, to do things like playing cards and smiley faces. And if you've ever watched an IBM PC crash really, really hard, you get a screen full of little smiley faces and playing cards and gibberish, because that is just random noise being rendered with code page 437. Now, a whole bunch of different organizations all over the world, they came up with their own code pages for it. Does anyone here speak or read Russian? Marvelous. So there was an American standard for writing Russian in ASCII, which didn't work. And the reason it didn't work is that it encoded, say, the Russian word privyet, and it would give a code point to each of these, but it was quite common at the time for email systems and networks and word processors to assume that your file was only 7-bit ASCII, and so they would use the 8th bit for things like parity checking or marking whether something had been archived. So we got our 8 bits of encoding. Some email system strips off the 8th bit, renders it back into ASCII, we get gibberish. It's completely unreadable. So the Russians went, we're not using the American system, it doesn't work. We're going to use our system. We're going to use the Kod Obnerma Informacja 8-bit, the 8-bit encoding system, which is brilliant, because what it did is it took the characters of the Russian alphabet and encoded them into English letters that kind of sound the same. So that although the document had been mangled, one, you could tell it had been mangled because the capitals came out lowercase and vice versa, but you could look at it and you're like, Privyet, okay, I think I know what's going on here, which I just think is a beautiful system. Anyway, lots of different people came up with lots of different code pages. And if you go on Wikipedia right now and look at code pages, this is the list of code pages that have Wikipedia articles. So we've got the IBM ones, we've got the Apple ones, we've got the DOS ones, we've got the ones that shipped with IBM AX, which is still supported in some systems. We've got the tech typesetting system. This is chaos. For a while, it was chaos we kind of lived with, because you could mix like English and Hebrew in a document, but if you wanted English and Hebrew and Arabic, you had to write pages in separate documents and then put them together after you'd printed them. But that was kind of fine, because we used to print stuff. But then we invented the web, and we started using email, and we connected all the computers together, and we needed a way that they could communicate with each other. And so the Unicode Consortium, the Unified Coding System Consortium, was founded in 1991. And their mission statement: to provide a single consistent way to represent each letter and symbol needed for all human languages across all computers and devices. Ambitious, huh? Now, let's pick that apart. A single consistent way to represent each letter and symbol. First of all, we've got to figure out, what is a letter? What is a symbol? All human languages, not just the ones we have now, the ones we used to have as well, and the ones we haven't invented yet. And all computers and devices, well, the only way to do that is to make something that is very, very good, make it the easiest solution to problems people have, and make it completely free. And the astonishing thing about Unicode is they succeeded. The reason why the web works, the reason why email works, is that Unicode did a brilliant job on this. Now, letters. Do you think these two strings are the same? These are, they look the same. They're the same shapes, but they're not the same sounds, they're not the same word, and they're not the same language. The top one is hor, which is horosho, which is Russian, and the bottom one is the XOP in the English word exoplanet. What about these two? Now, these are the same sound. These are both t, because the top one is the T in tiger and the bottom is the T in tiger, and they mean the same thing, and they're the same shape representing the same noise. Are they the same letter? This is what Unicode had to figure out. And they went, no, they are not the same letter, because one of them, when this shape makes the T sound in English, that is a different letter to when this shape makes the T sound in Russian or in Cyrillic or Slavic languages. And so they had to come up with encoding systems for capturing different languages, different alphabets. Now, I am British English, so when I travel, my brain tends to see words like this and ignore the bits that I don't recognize. And so I will look at this and my brain will just go, oh, well, obviously that says harphoner. And if any of you read Norwegian, it's, I think harphoner is a better pronunciation. It's the Norwegian word for hairdryer. And so I ask for a harphoner and everyone laughs. But you know, we have, let me introduce you to some friends of mine. So this is Francois Borda, who's an archaeologist, and this is Motley Crue. And Francois, the archaeologist, went to the Motley Crue concert. Now, this sentence is in English, but there are characters here which are not part of the English alphabet. So what do? Where do we get these characters from? Now, in English, we borrow them. We pull them in from different character sets and we just set them in what we're doing. But then we can get into some confusion about, well, if we can't render the little sedia, the tail there, is it okay just to put a C there? What do we do if we can't encode these things faithfully? This is Magnus Mårtensson. No, this is Magnus Mårtensson. Magnus is Swedish. He's an Azure MVP, does a whole bunch of conference travel. Some of you may have met him. A couple of years back, Magnus is on his way to the US, and he gets into a spot of difficulty at passport control. Now, Magnus has a Swedish passport, and the rules of Swedish orthography say that if you have to turn the letter O, which is the A with a circle, into ASCII, you do it by doubling up the A, M-A-A. Whereas the people who had printed Magnus' airline ticket, they're like, we'll just take the circle off, nobody cares about the circle. So Magnus ends up trying to get into the United States with a passport which does not exactly match the name printed on his airline ticket. And the American authorities, as you know, are famously educated and forgiving when it comes to immigration and other cultures. But this gets us into a whole world of cultural weirdness. Here is a list of cities in Europe, and we are going to take this list and we are going to put it into a SQL Server database. And we are going to insert Berlin, Aachen, Zurich, Aarhus, and Örebro into our database. And then we are going to go select star from cities, and there they are. And then we are going to select star from cities where name equals Örebro. And hang on, that's interesting. Maybe it's case sensitive. Oh, okay. What do you think is the problem here? The umlaut. It's not the same O, or is it the same O? Well, it turns out that Unicode does not tell us whether it's the same O or not. Unicode says you are going to need to figure this one out for yourself. Because if you say, compare Örebro to Örebro, yes, no, it's not the same. But if we say, please use the Latin General 1 case-insensitive, accent-insensitive collation rules, they are then considered the same. It gets better. Let's talk about alphabetical order. Now, here's our list of cities. And if we order them by name, we get Aachen, Aarhus, Berlin, Örebro, Zurich. Okay, but now we are going to do them alphabetically according to the Finnish and Swedish case-insensitive collation, which gives us Örebro is now after Zurich, because in the Finnish and Swedish alphabet, O with an umlaut is the 28th letter of the alphabet after Z. Now, if we do the same thing with the Danish and Norwegian collation, Aachen and Aarhus now go to the end. Now, you're looking at that and you're thinking, what? If you put Athens is at the beginning, and so you're thinking, what's going on here? Now, this is Aarhus. It is the second largest city in Denmark, and it was officially spelled Aarhus with this letter from 1948 until 2011. The reason why, in 1948, there was a thing called the Danish Spelling Reform, and Denmark basically, for political reasons I'm sure you can work out, went, it's 1948, we don't want to be like German anymore, we want to be more like the Swedes, because people like the Swedes, so we are going to stop using Germanic spellings in our place names. We are going to add 3 new letters to the Danish alphabet, and any towns that start with AA will now start with this letter O. So Aarhus became Aarhus, different spelling, and because the A with a circle is now the 25th letter, 27th letter of their alphabet, 29th letter of their alphabet, it goes at the end. Then in 2011, the people of Aarhus voted to change the spelling back, but not change the alphabetical order. So this list is in alphabetical order in Denmark, because Aachen is in Germany, and so that goes at the beginning, but Aarhus is in Denmark. This is the rule of Danish and Norwegian orthography, is things starting AA go at the end of the alphabet if they are Scandinavian things, but not if they are foreign things. And this makes perfect sense to anybody who grew up there. They're like, why would this be a problem? And you're looking at them like, it's a problem because you literally can't get it right using the information in the text. You need to go, and if somebody decides they're going to call their kid, Ornørn or something, you're like, well, is that a German Ornørn or a Norwegian Ornørn? Because where the kid goes in the school register will depend on whether it's a Scandinavian or a German or at the beginning. Now, if you do find you've got to get this stuff right, the only way to actually do it is that you need to put another column in your database that's, okay, this is what you show the humans, and this is what the machines can use to get things in the right order. And you override the sort order. If any of you has ever worked on something like a British telephone directory where we have these bizarre rules about McGregor and MacDonald, because Mac is the AC and Mac doesn't count for alphabetical ordering purposes, according to some editorial styles. So we get this sort of very, very complicated thing. If you're using Norwegian language Windows and you look at a file explorer, aardvark will be at the end. This is why. And what it kind of drives home to me, we have all this complexity that when you first encounter it can be absolutely baffling until you understand the forces behind it, the cultural and the historic reasons for doing this. A lot of people are like, I work in tech, I don't really do politics. Well, tech is full of politics and history and culture and all these really complicated things. World War II is the reason why aardvark appears at the end of the file list on Norwegian Windows. And once you understand that, you're like, well, would there have been a good time to change it? Probably not. Would I have done it differently if I was there when it happened? Probably not. I guess we're just stuck with it. Let's go back to our friend the C Sedir. Now, in Unicode, we can write this as this character here. This is code point U00C7, and that is this character. Or we can take a regular ASCII-flavored C and we can put one of these on it. This is called a combining character. And a combining character basically says, take whatever you just draw and put one of these on it. And the great thing about combining characters is that you can add combining characters to combining characters to combining characters to combining characters until you end up with what we know on the internet as Zalgo text, which, depending on your operating system, will either render as plain ASCII, it'll render like this, or it'll crash your phone. And this is just stacking up these combining characters that, like this little one here, that just says, hey, whatever you just drew, put one of these, like a little sideways eye, right on the top of it. And you can keep stacking these things up. Now, once you get into working with these combining characters, that starts to raise a whole new set of questions about equality. So this is Francois set two different ways. The top one, we have the code point C with Sedir. The bottom one, we've got a C and a combining character. Are they the same? Are these strings equivalent? Well, a binary comparison says, no, they're not. I mean, they're not even the same length. Look at this. But that doesn't work. We don't want a scenario where we can't find Francois in Google because we forgot to type the little Sedir. We want to kind of, get a level of abstraction and approximation that makes these systems usable for us imperfect humans. Now, again, Unicode didn't solve the problem. What they did is they gave us a set of choices and said, it's up to you which ones of these you use. And they created normalization forms. So there are 4 forms of normalization in Unicode. There is composed and decomposed. Composed means you squish this down until it is the smallest number of code points. If you've got a C with an accent, see if there's a single character that will replace that pair. See if there's a single character that will replace 2, 3, 4 character sequences. Decomposed is the opposite. Stretch it out as much as you can. Split out all the accents. And then there is the K here stands for canonical, because C was already being used for composed. And canonical means don't look at what it actually, the specific letters. Look at the underlying meaning of those letters and tell us whether that works out the same. So if we have the word bunya, which is, it's Romanian for hello, I think, because the last time I did this talk was in Romania. This is 2 different strings that both say the same thing. They mean the same thing, they render the same. Are they the same thing? Well, let's have a look. We're going to run our little program and see what we got there. And according to this, those are not the same string. S1 equals S2, that's false. Binary comparison says they are not the same. But under canonical composition and canonical decomposition, all 4 forms say these things are the same. So if you got one of these and you got the other one, treat them as equivalent. There are also Unicode sets like this one here, which is a set of letters surrounded by circles. Now, obviously these aren't the same glyph, they aren't the same shape, but they do represent the same letter. And so if we run a comparison across this one, what we get is that under the canonical forms, they are equal, and under the non-canonical forms, they are not. It's like, yeah, that says salute, but it's a different way of writing salute. So you need to tell me what rules are at work here when it comes to deciding if these things are the same. Now, I learned about Unicode and encoding systems and everything in a hurry. I had a very, very rapid crash course introduction to text encoding about 5 years ago when I got into work one morning and somebody said, dude, I think we've been hacked. Now, when you work in IT, people get hacked all the time, right? I've been hacked. No, you haven't. You've accidentally revealed codes. I've been hacked. No, right-click view source. I told you not to do that. But on this occasion, the person who said, I think we've been hacked, was one of the best security engineers I have ever worked with. And I said, why do you think we've been hacked, Chris? And Chris said, there is Chinese in the Windows event logs. And I looked in the event logs, and yes, there was Chinese. Now, the nice thing about working with a good team is you're like, right, you go and start looking through the firewall logs, see if there's any suspicious activity. You go and search the database, see if you can find Chinese in any of the tables or any of the transaction logs. See if this stuff is something that has been put in there by some kind of injection attack. You let everyone know we might be issuing a press release later today about a data breach, and I'm going to sit and I'm going to post about it on Twitter. Now, you might not think that posting on Twitter is a valid diagnostic technique, but I have some very smart, helpful people following me on Twitter, because within a minute, I got someone saying, that looks like a Unicode mapping error, and someone else saying, no, the low bits are all none, so this is probably UTF-16LE being mistaken for UTF-16BE. And I'm going, yes, I know these words. So I Google UTF-16LE, BE, WTF, what is going on here? And this is what I learned. Internally, Windows and Java and JavaScript, they use UTF-16. All the letters in Windows, internally in your computer's memory, they are stored as a pair of bytes. So they are 16 bits. And so the word delete looks like this. That is 0044 because it's ASCII 44. 0065, 0060. Now, the thing about UTF-16 is you need to know which way round it goes. If it gets reversed, what you get is Mandarin Chinese come out the other side. This one, I ran this through Google Translate just because I was like, I need all the information I can get. This is the Han Chinese character for placing a pearl in the mouth of a deceased relative. And I'm like, either this is a very weird ransom note, and this one is to prepare a duck for ritual slaughter. So I'm thinking, I don't think this is anyone trying to send us a message. So the question is, right, this is pretty much what's going on, because this is the Chinese we saw, and it was the word delete that had been bit swapped. I'm like, why are bits getting swapped on our production database? Now, it wasn't that the encoding had gone wrong. There was a network switch, a virtual network switch in our hosting center that had got a fault, and it was dropping 1 byte from the byte stream. Every couple of minutes, it would just drop 1. And when it dropped 1, everything would get shuffled sideways, and the rest of the stream would come out as Chinese, and a couple of minutes later, it would drop another one, and everything would shuffle over again, and it would fix itself. We had some very, very harsh words with the data center people about that, and eventually migrated, and when we went to AWS, we didn't have this problem anymore. But that was my introduction to the world of encoding, because we have this, interesting challenge when it comes to encoding things, which is, in theory, we have enough space to encode everything, because the Unicode standard says you can use up to 8 bytes to encode 1 character. But if you did that with everything, think about something like a web page. Even a web page that is written in, say, Korean, all the markup is still ASCII. All of the JavaScript and the CSS and the metadata that goes with it, that's still ASCII. We don't want that ASCII to be 8 times bigger than it needs to be, because that's a massively inefficient use of memory and bandwidth. And so the Unicode Consortium, they came up with something I think is absolutely brilliant. There was a problem with Microsoft PowerPoint. Will attempt to recover your work, but recent changes may be lost. Well, that's interesting. What do you think? Is this going to work? Oh, you don't get this on Zoom. Where were we? Where were we? Yes. There we go. Oh, look at that. Ta-da! UTF-8. UTF-8 encoding is absolutely brilliant. What it basically says is, look, if you've got a bunch of bytes in a file, any byte that starts with a 0, any byte that starts with a 0, that's 7-bit ASCII, same as it was in 1965. Don't mess with the stuff that already works. Any byte that starts with a 1 is part of a multi-byte sequence. If it starts with 1, 0, you are in the middle of a letter. You need to back up a little bit until you find 1, 1. And if you find 1, 1, 0, that is the start of a 2-byte sequence. If you find 1, 1, 1, 0, that's the start of a 3-byte sequence. If you find 1, 1, 1, 0, that is the start of a 4-byte sequence. They kind of cut off there because if you go 5, 6, 7, 8, you end up with things that you can't translate into any other encoding. This one here, the bottom one, you can round trip that to what's called UTF-32, which is 4 bytes for every bit, which Windows and Java and most platforms will support, although they don't use it by default. And this is fantastic because this gives us a consistent, optimized, efficient encoding system for all the languages we've already got, all of the human languages, from history, like ancient Sumerian and Egyptian hieroglyphics, because people study this stuff, and they need to be able to store their research on a computer somewhere. And all the languages and alphabets that we are still inventing. And you're probably thinking, but we're not inventing alphabets, are we? Well, we are. There is an alphabet invented in my lifetime, which I guarantee most people in this room will have used today, which is the alphabet called emoji. Emoji came out of a Japanese mobile phone information system in the late 1990s. They wanted a way of doing things like traffic and weather forecasting that was a little bit more interesting, and so they created, the project was a thing called Docomo, and they created this set of 176 colored emoji, which is now on display at the Museum of Modern Art in New York. And it was massive in Japan, and everyone loved it, which meant that when Apple wanted to sell iPhone in Japan in 2008, they had to add emoji support, otherwise no one was going to buy it. And then people around the world worked out that if they went into their iPhone and they enabled Japanese as an alternative language, they got the emoji keyboard, and they started sending smiley faces to their friends, and their friends started sending back, "How did you do that? That's the coolest thing I've ever seen," because we were easily impressed in 2008. And very, very quickly, emoji became a de facto standard. It wasn't actually a standard. It didn't get added to Unicode for about another 8 years. But as emoji spread around the world, people started asking questions. They're like, why can I send someone sushi, but I can't send them tacos? Why are all of the professions in this little yellow Simpsons men, and they're always men? And who's making the decisions around what kind of people and cultures get to be supported by their own emoji? Now, in 2015, Unicode took a really, really big step towards making emoji more inclusive, because they came up with the idea, what if we could take a character, and just like we used combining characters to put accents on letters, we could use combining characters to modify the skin tone of things like, thumbs up and smiley faces and stuff. And they did. And today, every year they announce a new set of characters that are being added to emoji. This is the set that was added last year. And you're looking at that and thinking, there's no way there are code points for every one of these combinations of ethnicity and gender identity and family configuration and even what color you want your cat to be in the emoji thing. But the solution that they've come up with for these kinds of things, I think, is quite brilliant. Basically, you can combine things. So the female astronaut emoji, the code point for that, is actually the emoji for woman, plus a thing called a zwidge, a zero-width joiner, and then the emoji for a rocket. And if your handset supports it, it knows that woman plus rocket equals female astronaut. Draw that one instead, and you can then go, well, if we want to do an emoji of Mae Jemison, who was one of the space shuttle commanders, that's woman plus the skin tone plus the zero-width joiner plus the rocket. And so all of these combinations that are being added to emoji for different kinds of relationships and stuff is all zero-width joiners being applied in interesting ways. Now, when we talk about flags, it gets really interesting. Anyone recognize this flag? It's the flag of Belarus. And the flag of Belarus, in Unicode, there is a block of letters, which are the letters that you use to make flags with. And so we take the regional indicator symbol letter B and the regional indicator symbol letter Y, we put those two together, and if your handset supports it, it's like, I know that one, that's the flag of Belarus. This works for countries that have an ISO country code. England does not have an ISO country code. There is another block of letters in the Unicode spec which are known as the tags. And these were put in case we needed them for anything. And then they were taken out because we weren't using them for anything. And then they were put back in a hurry when it turned out actually we were using them for stuff after all. And this is how you do regional flags which aren't countries. The GBENG gives you Great Britain, England. That's how you do that flag. Same for Wales, same for Scotland, same for Texas. Is part of the Unicode set. And the pride flag is a white flag with a zeroth joiner and a rainbow, which I think is rather nice. Now, flags are political. Flags are complicated. Does anyone recognize this flag? This is the flag of Taiwan, except Taiwan's not called Taiwan. Taiwan is the Republic of China. That is the official name of the country we know as Taiwan. And the idea of Taiwan being a country is controversial in the People's Republic of China, which is the big one on the mainland that everyone thinks of as China. Now, if you go onto your iPhone and you go into the flags emoji, you can type the flag of Taiwan. But then if you go into your settings and you change your phone's region to be China mainland, and you go back into your emoji, the flag has disappeared. And it does not appear on the keyboard anymore because this was Apple's solution to how to sell iPhones to the 3 billion people living in China without upsetting the Chinese government. Because money talks, I guess. Now, Windows solves this in a much more interesting way. It just goes, no, you are not having any regional flags. If you look at my Twitter feed, I've got a little EU flag in there. And when you view it on the web, that's actually a PNG being drawn by Twitter's web code. If you go in to edit it, what you get there is the letters EU, because that is the regional indicator letter E, the regional indicator letter U. On most devices, that will render as the flag of the European Union. On Windows, it's like, no, that's just E and U. The only flags that work on Windows are the pride flag, the trans flag, and the pirate flag. So Windows says, no countries allowed, but gay trans pirates, bring it on. Which, you know, it's a position I can kind of get behind. Now, I want to wrap up today by sharing one more cool thing about text and encoding with all of you, which is if you take a look at the logo type for my company and you look closely at the TI here, you see that kind of stuck together, which I think is quite cool because I like things like that. Now, that is just ASCII. That is URSATILE. There is nothing special about it. This effect is called a ligature, and it's a property of the font. There is a rule in that typeface, the typeface is called Lato, that says if you see a T and an I, draw them together as this special symbol instead. And ligatures are brilliant because we can use ligatures to write code. Take a look at this chunk of code here. This is FizzBuzz in F#. Now, what's happening in the actual file here is this. It is regular ASCII pipes and arrows and things, but this is using a font called FireCode, and FireCode has programming ligatures in it that say things like, well, if you get a pipe followed by a wedge character, draw it as this little triangle, and draw special magic arrows. And so FireCode doesn't mess with your source code, doesn't change anything about your actual project, it just changes the way they look, and it makes them, improves readability, it makes it easier in things like JavaScript to tell the difference between a double and a triple equals. It's absolutely fantastic. So go and check out FireCode. You can run it on, because it's a font, you can run it on just about anything. Visual Studio, VS Code, WebStorm, all the JetBrains products. It's very, very cool. Now, last thing I'm going to tell you today is a couple of years ago, I went to Belarus. And I'm walking around Belarus and realizing that I can't read Belarusian or Russian yet. I started learning after that trip. And then I noticed this is really weird. I can't read the menus. This, by the way, is how you say Jamie Oliver in Russian there. I can't read the menus, I can't read the road signs, but I can read all the license plates on the cars. I'm thinking, why would Belarus use English license plates? Now, there is a thing called the Vienna Accord on Road Traffic, which was signed actually in 1965, the same year as ASCII. And it's a set of rules about what you need to do if you want to drive internationally with your car. And one of the things the Vienna Convention says is that you must only have the Latin ASCII character set on your license plates. Now, in 1965, Belarusian license plates looked like this. Because in 1965, if you wanted to drive your car out of the Soviet Union, license plates were the least of your problems. And if you could get the necessary permits and the license and approval to travel from the Communist Party and everything, when you got to the border, they would give you temporary license plates to use while you were outside the Soviet Union. And if you didn't bring them back, you were going to be in a lot of trouble. But then when the Soviet Union ended in the 1990s and all of the various states became independent, they all reformed their traffic licensing system. And today, in Ukraine and Belarus and Russia, the license plates look like this. And the way they did it is they took the Cyrillic alphabet and they took the Latin alphabet, and they identified the set of glyphs, not letters, glyphs, shapes, that are common to both of those alphabets, and they said, this is what we are going to use on our license plates. And if you take that set of letters and you mix them up and rearrange them a little bit, they spell PIKE MATCHBOX. And so I want you to remember that, because next time someone says, I'm going to send you a plain text file, say to them, do you know about PIKE MATCHBOX? And if they say yes, then it means they've seen this talk. And they know about big endian and little endian encoding and canonical decomposition forms and combining and Chinese in the event logs, and that when it comes to plain text, they know what they're talking about. And if they say, what's PIKE MATCHBOX, then you could be getting just about anything. Thank you very much.